So what are intermolecular forces? Intermolecular forces are forces between molecules. The prefix inter means between. Intermolecular is between molecules. We can generalize it to be between particles because we're not always dealing with a molecule. Let's contrast that with something called intramolecular forces. Now, you've already studied intramolecular forces, whether or not you called it that. The prefix intra means within, so these are forces within the molecule. These are bonds. An actual honest-to-goodness bond between two atoms, a covalent bond, is an attraction within that molecule, and we've studied that before when we've drawn pictures of us. These are Lewis structures. So in chemistry, an intramolecular force is a bond within a molecule. That's not what we're talking about in this chapter. In this chapter, we're talking about intermolecular forces, which is the attraction between two different particles in a sample. So now we have more than one of these molecules or particles, and we're looking at the attractions between the particles. And the reason why we're looking at these attractions is because we're going to discuss them in terms of why are some things solids, some things liquids, some things gases. Why does that occur? So let's start talking about what the intermolecular forces are. The first one I want to look at is something called dipole forces. You may recall when you studied Lewis structures that you talked about the fact that some molecules are polar, which means they have a dipole moment, and yes, you still need to remember that. For example, let's look at the molecule HCl. Now, we're not talking about hydrochloric acid. I want the pure substance HCl. That means I have the covalently bonded molecule, hydrogen and chlorine bonded to each other, and the Lewis structure would have some lone pairs on the chlorine. The Lewis structure would look something like this. As a pure substance, if I had a jar of HCl at this, right here in the classroom, it would be a gas. That means that it's going to look kind of like the picture that we had of the gas, where the particles were very far apart. Now, there are intermolecular forces. There are forces of attractions between the HCl molecules, and they are because of the dipole moments of the molecules. Recall from when you studied the Lewis structures that the hydrogen is partial positive, the chlorine is partial negative because of the electronegativity differences. We can represent that a couple different ways. On the top here we have our partial plus and partial minus drawn. On the bottom we have another way to represent who the partial positive guy is and who the partial negative guy is. And in a sample of HCl, we have lots and lots of these molecules floating around in our container. And all of these molecules are polar with a partial positive side and a partial negative side. We all know that what makes the world go round is the attraction of positives and negatives. And so what we see in this container of HCl is we see an attraction between the partial negative side of one molecule to the partial positive side of a separate molecule. In green, we see our intermolecular force, our IM force, intermolecular. This is our intermolecular force. It's between these two molecules, and it is an attraction between the partial negative of one molecule and the partial positive of the other. Likewise, we have an attraction between these two molecules, between the partial negative of one side of one molecule and the partial positive of a second molecule. This is also an intermolecular force. As opposed to the intramolecular force, I know I crossed it out, but let me point at it one more time. That would be the actual bond between the hydrogen and the chlorine. So the actual bond between the hydrogen and chlorine is our intramolecular force. It's within the molecule of HCl. The green dashes, and we usually do represent them as dashes, a dashed line, I should say, rather than simply one dash. This ... dash line is an intermolecular force between two different molecules. Now, the stronger this intermolecular force between the two molecules, the more likely these two molecules are going to be closer together. So a weaker intermolecular force will allow those molecules to get further apart. the stronger intermolecular force is going to tend to pull them closer together. That force of attraction will pull them closer together, and so you can start to see sort of take shape what the difference between a solid, a liquid, and a gas would be. This intermolecular force in green is called a dipole force. Sometimes we refer to it as a dipole-dipole force. We actually say it twice because it is between two different molecules which both have a dipole moment. So this is an example of a dipole force. All right, let me clear the page and get started on a second type of intermolecular force. We can go a little quicker on this one because it uses a lot of what we just talked about. In some molecules that have a dipole force that we just talked about, some molecules that have this dipole force, like for example HF, this is another example of a molecule that is polar, so there is a partial positive on one end, a partial negative on the other end because of the dipole moment. In a sample of HF in a container, I'll have lots of these molecules floating around, bopping around. We will see this force of attraction between the partial positive of one side of one molecule and the partial negative of a second molecule, just like we saw with the HCl. So we'll see intermolecular forces, these forces of attractions between the two different molecules. Now it turns out in HF, as opposed to HCl, this intermolecular force is much stronger than it was in HCl. This particular intermolecular force is so much stronger than the dipole force we saw in HCl that we've given it a separate name. This second type of intermolecular force is called hydrogen bonding. Now let me caution you, it is not a bond. It is an intermolecular force, and we've already talked about the difference between an intermolecular force and an intramolecular force. But the name of this type of force is indeed hydrogen bonding, or sometimes we'll just say it's an H bond, but it's not a bond. Must be a biologist that named it or something like that. It is a type of intermolecular force. It is stronger than a dipole force, but it is similar enough to a dipole force that we call it a special case of dipole force. This is actually a special case of a dipole force. A special case that is stronger, and it occurs, we see it in samples where we have a hydrogen bonded to a fluorine, or a hydrogen bonded to a nitrogen, or a hydrogen bonded to an oxygen. If you have a molecule with a hydrogen bonded to fluorine, or a hydrogen bonded to nitrogen, or a hydrogen bonded to oxygen, we see this special intermolecular force, this special case of dipole force. We see hydrogen bonding. It's a particularly strong dipole force. In HN, this occurs in molecules like ammonia. The molecule of ammonia looks like this in its Lewis structure. Remember that when we draw the Lewis structure, we draw it flat, but this is actually a trigonal, pyramidal, or pyramidal molecule. In 3 dimensions, it looks something like this. It's a little pyramid with the lone pair on one side. We have a dipole moment in this molecule. The nitrogen's partial negative, the hydrogens are partial positive. And so a second molecule of ammonia can be attracted to the first molecule of ammonia in an attraction between the partial positive of the hydrogen on the one molecule of ammonia and the partial negative on a nitrogen of a second molecule of ammonia. Notice that this is not the hydrogen bond. This bond between nitrogen and hydrogen is actually the bond, the intramolecular force between the nitrogen and hydrogen. It's a legitimate bond. This dashed line between two different molecules is our intermolecular force called hydrogen bonding. So hydrogen bonding is a type of intermolecular force. It's a special type of dipole force, or a special case of a dipole force, and it is stronger than an ordinary dipole force, but it's an attraction between those two molecules.